Hey everyone. Okay, another day, another Leetcode problem. So today we're going to be solving 3464 that's maximize the distance between points on a square. So what this problem is asking us is, so we're going to be given an array of points, which are x1, y1 coordinates, and we're going to be given a value k, which is the number of points we have to select from this array of points, and we're going to be given the value of a side. So the question is asking us, return the maximum possible minimum Manhattan distance between the selected k points. Okay, this sounds very confusing, and this is a Leetcode hard problem, as we can see. So I'm just going to go ahead and explain it here. Let's get a hold of the intuition, solve like an example, then we'll go to the code, and I hope I can do a good job at explaining this. It is a bit confusing. Okay, so the question basically asks us that we have to maximize the minimum distance between points on a square. Okay, so you are given points on the boundary of a square, and you need to choose k points out of these. So essentially the goal is make the minimum distance between any 2 points the maximum. All right, it's still confusing, so let's go ahead and probably just try to draw it out and see. Okay, I have 0 here. This is my x-axis. This is my y-axis. Let's say this is 2 here. This is 2 here. And yeah, let's consider a few points over here. Let's consider one over here, here. Let's say this is A. Let's say another point B over here. This is C. This is D. Let's say there's another E over here and an F. Okay, so let's say this is at a distance of 1, these here. Now, I am given 6 points, as we can see. And let's say k, let's assume k is equal to 4. So I need to choose 4 of these, 4 amongst these 6 points. Okay, so the goal is to minimize the distance between the closest points. Let's consider an example where we take these points. Let's say we take A, B, C, and D. All right, so if we check that and I draw it again over here, what we have is A is here, B is here, C is here, and D is here. Now, if we look at the closest points over here, it's A and B, and we can see that the distance between the closest points would be our eventual answer. So as we can see, that's not really in accordance to our goal of trying to minimize the distance between the closest points. So this was not the optimal answer for this problem. So now let's go ahead and look at a few different points. Okay, so let's consider A, C, D, and F. So now if I draw that, we have, this is A, C, this is D, and this is F. And because they're at a distance, like this is 1, 1, 1, 1 here, I can see that all of the points are equidistant. So the 4 points are equidistant, and the distance between any 2 points is basically 1 plus 1. So eventually that's the value of side right here. So the answer would be equal to 2. And if you try it in any possible way between these points, this is the optimal answer that we're supposed to get. So yeah, that's an answer of 2. Now the question has mentioned we want to get, what does it say here? The minimum Manhattan distance between these k selected points. Okay, so let's just understand what Manhattan distance actually is. So if I have 2 points, x1, y1, and x2, y2 on a coordinate. So what we see here is the distance between those 2 points, the Manhattan distance between them is the absolute difference between x1 and x2, and the summation of that, as well as the absolute difference between y1 and y2. And that's how we get our Manhattan distance. So let's just probably take an example here. And also, I've mentioned here as an analogy, you can only walk in straight grid paths. Okay, so assume it's like a city. I believe that's why it has the word Manhattan in it. So you're not allowed to take the displacement and go in like diagonal shortcuts and stuff. So if you have a square here and you have a point A over here at 0, 0, and let's say you have a point B over here, which is at like, 2, 1, the Manhattan distance would be this distance effectively, okay? So you're not allowed to take the shortcut and go like this. You have another point C here, this is the Manhattan distance. You have another point D. This is the Manhattan distance. So yeah, that's essentially what it means. And our goal here is to try to maximize, maximize the possible minimum Manhattan distance. So yeah, essentially that's where they're asking for between the closest 2 points, the Manhattan distance between even the closest 2 points of those K points selected has to be maximized. So that's essentially like saying, let's say if I had like a square table and I was trying to seat 4 people here, 4 or 5 people. Let's say I placed one here, one here, one here, one here, and one here. Let's say this was the most optimal arrangement pattern. So the closest people here are probably these 2. And in this case, the distance between even the closest 2 people has to be big. So even they have to be far away. Okay, so what are we trying to maximize? We want to maximize the minimum distance between any 2 points. So like I mentioned, the analogy here is even the closest seated members are far away from each other. Okay. So I'm assuming you guys now understand the question. And so I'll tell you why this is a binary search problem. If you are used to solving problems regularly and you have seen patterns, then the concept of maximizing a minimum or minimizing a maximum is always binary search. I mean, there could be other possible ways to do it, but binary search is definitely an option here. So you know that when you're trying to minimize or maximize something, you are dealing with a continuous stream of numbers, which are preferably sorted, always sorted. So when you are dealing with that stream of numbers, you know that there's a possibility that you could go on trying to optimize the way where you actually find that right answer. So binary search on the answer itself. So it would be like this. So you try out a distance D. So we're trying to maximize this distance, right? You try out this distance D, and then you can check. If I use my my distance, my minimum distance between 2 points as this value D, am I capable of placing K points within the given space that I have? And if you are capable, then you're gonna try to increase that value of the minimum distance. Or else if it's not possible, you're trying to reduce that minimum distance value. And the goal here is to maximize that minimum distance value. So we're trying to deal with here is a binary search where we get an answer and then when we try to look to the right to find a better answer. So yeah, that is why binary search. Now, binary search is very efficient when you have, like I mentioned, a continuous stream of numbers which are sorted. And in this problem, as we can see, the points that we are given are in the form of they're 2-dimensional. There's an x and y coordinate. So we're gonna do kind of like a handy trick here where we'll be converting these points into a 1-dimensional, like a 2-dimensional coordinate point into like a 1-dimensional line. And let's see how that's going to be done here. So let's look at this the square over here. Let's say there is a point here. There's a point A, there's a point B, C, and let's say D. Now, if I look at the point A, I know its coordinate is, it's 0, comma, whatever y value is here. So, yeah, I have that here. So let's see. If I see that my x-coordinate is equal to 0, I can tell that the distance I'm actually adding here is whatever y value is there, okay? So let's have something like, let's just call it, I want to see what naming convention I've used here. Okay, it's perimeter positions because it's on the perimeter. Okay, perimeter positions, we want to append y, okay? Now let's look at point B. Now I see that point B, the y value of point B is basically side. So side is a value that's given to us as they've stated. So I know if it's side, then the distance I have to travel to come to B is this, which is basically side plus the x coordinate of it. So I can say if y is equal to side, then perimeter positions append side plus x. Okay, now let's look at C. So I see that C is at a distance in X. The value of X is equal to side. So if I see that, I can see that over here, it's actually 3 times the side minus whatever Y coordinate was mentioned, right? So I can write that as if X is equal to side, then I want to do perimeter positions dot append 3 times of the side subtracting whatever Y value I had. And the other possibility is that it's D, and D is basically a value of X. But since we're going clockwise, I can just write that as else perimeter positions dot append 4 times of the side minus our X value here. So it's like this distance here. Okay. So this is how we're gonna get values into a 1D form in the form of a straight line. And one thing you might ask now is, so if we convert it into a straight line, how are we going to have our circular nature? Because these points are actually on a square, which is kind of like a circle, right? If you look at it, the points are connected to each other. So the first point and the last point would be connected. So even if we're converting to a straight line, it's actually a loop and it's not actually a straight line. So the first and the last points are close in reality. So let's look at how this is like converted into a straight line. As I can see, my point A, B, C, D, so this is 2, this value is 1. So if I convert this and I have it as 0, my point A is at a distance of 1. Let me just go ahead and mark these 3, 4, 5, 6, 7, 8. Okay. So my point A is at a distance of 1. And then I see my point B is 1 plus 1 plus 1 here. So it's 0, 1, I have at 3, I have B over here. Then again for 5, so at 5 I have C, and then again at 7 I have my D value over here. So this is how it looks. And actually if you look at this, the 0.7 and the 0.1 over here look like they're very far away. But in reality, since this is a circle, we can see that D and A are actually close by. So we need to consider that and make sure that we're taking into accountability the circular nature of these points here. So we want to restrict it, and I'll show you guys why exactly. So we want to restrict it such that we don't cross over. So we don't cross over here and kind of loop back to this. We want to make sure that we have like a hard rule here that prevents us from doing that. So let's say our start is 0 over here. And let's say the whole perimeter, as we can see, the perimeter is 8. And let's consider the minimum distance to be 2 and K is 4. So we want to fit 4 points in the circular nature such that the minimum distance between any 2 points is actually 2. So I can do this. I can start from A being positioned at the start, which is 0. Again, let's just go ahead. Okay, let's just mark these here to make sure this is 0, 1, 2, 3, 4, 5, 6, 7. Okay, so the next point after 0 would have to be at a distance 2, right? Because that's the minimum distance. I get my point B here, then another distance over here. It can get my point C here, another distance of 2 over here. It can get D, and then again, as I see, the minimum distance still here is maintained as 2. Now in this case, it works, okay? So 2 might be my answer, and I can consider 2, and I can try increasing from 2 because we're doing a binary search for optimization. So let's say I go to the value 3, all right? So I'm gonna try to keep A here, and then I'm gonna go 3 spaces. So I'll be coming here. So I get my B value here. I try another 3 spaces. I come to 6 here. So that's my C, but I see that I'm trying to fit K different points, which is 4 here. If I come to 6, then I see that the distance between 6 and my next point should actually be 3, but my distance has become 2 here. And if I do this, then I'm actually making my answer 2 from 3. Like I'm not able to fit the right number of points because I have only 3 points. Also, the distance has been minimized between them instead of being maximized. So this is the wrong answer. If I keep doing this, I'll be shrinking that value. So I need to have some sort of rule here, right? That prevents me from doing that. So what rule we have is the maximum allowed distance, this value, has to be start. So in this case, we have start is 0 plus the perimeter value. So this perimeter value is 8 minus the minimum distance. So in this case, the minimum distance that we were trying to maintain was 3. So we get 8 minus 3. So the minimum, if I want to fit these points, like the last point can possibly be at a value of 5 here, 5 to 6, 6 to 7, then 7 back to 0. So this would maintain that 3 value there. So if I go to 6, I know that it's impossible. I will not be able to maintain that minimum value. So let's consider that this was 2. So in the case of 2, it would have been 6, right? So if I had maintained it at 6, like we did earlier, one position here, one here, one here, one here, then I'm able to maintain that minimum distance of 2. So yeah, this formula is important. We're going to use that to kind of make sure that this looping is correct. Okay, so this is more related to the code. So I think we'll go to the code and we'll then come back here so I can explain why this is the case. Okay, so what we're doing, this was the first step where we're actually taking perimeter positions. So yeah, this will just be an array. We're gonna take our points here, the points, as I mentioned, in the same way, they're gonna be converted and added to perimeter positions. So perimeter positions is basically our straight line, which has a circular nature. And let's take into accountability the perimeter. So the whole perimeter will be whatever side was given times 4, okay? Length of perimeter. Okay, we'll come back to this function of can place after this. So let's look at the binary search part here. So we have a left and we have a right. And now I want to tell you guys exactly why. Okay, so left, the value of left can be 1 because we're going to try to place at least one value here. And the right value will be side. And I'll tell you why. So this right here, this left and right, what we're trying to find here is that minimum distance that we have to maximize, right? So obviously the points have to be separated by some distance. That's why we've taken 1. We can't take 0 here. And why this is side, I'll tell you why it's side. So if we look at the conditions over here, it actually says that the points, I mentioned somewhere here that k is greater than or equal to 4. So the minimum value of k will always be 4. And if I want to, sorry, not a square, circle, not a circle, it's a square. If I want to maintain 4 points in a square, this is the most optimal way that I can do it. So the distance will have to be that of side. I cannot place it more than side because then that would mean there would become like another minimum distance, which is not correct. So yeah, the right most possible value, like the greatest possible value for right, will have to be side. Okay, so now we're going to do a binary search. We look for mid and we see, can I place this number of points? Is it possible? And if it's possible, that might be the best answer. And I'm going to look further to the right to see, can I look for a better value? So that's why I'm doing left is equal to mid plus 1. We're just discarding everything before that because we've already found a possible value. And then we're going to try to increase that value further. Or else if it's not possible, then we're going to try to decrease that minimum value. And then we return best. Okay, so let's look at this. We want to check if that distance D, that minimum distance D, is actually possible. And now what we do is for every position in perimeter positions. Okay, so perimeter positions was from this this square here, right? So it could have been jumbled up based on the way we kind of took those points or how the points were given. So we want to go ahead and sort that because that's going to be useful for us in terms of our later binary search. We're going to do that again. We're going to do a bisect. So what's happening here is for every start position, because it's in a circular nature, anything might be the start position. And from that start position, we want to take k points. So we're going to start from every start position in perimeter positions. And like I mentioned, the maximum allowed position of the last point, we're going to keep that handy. And then we're gonna keep a count and then a current. So current is the start position. And after we select the start position, we wanna look for still k minus 1 further points, okay? And yeah, let me just explain this here. I think it's better than I come back to this, okay? So the question is, why are we starting from each different point? Okay, so we don't know which point is actually gonna give us the best configuration. And that's why we want to go ahead and try all of them, all right? So you can try the first every point as the first chosen point, and then we can be greedy because we have sorted the array, right? We want to be greedy and take the exact next value, because obviously we've already decided what our minimum distance is. So if I take minimum distance is 2, and then the next point, let's say in 1, 3, 5, 7, let's say I skip 3 from 1 and I go to 5, like, why would I want to maximize the distance between the current point and the next point? Right? Because if I keep doing that, I might not be able to fit k points. And since the array is already sorted and we were able to fit that minimum distance, I just want to go ahead and take the very next point. And I'm being greedy here. So you have to always choose the next possible point as early as possible. And by the nature of like being greedy, this gives us the maximum chance to fit k points. Let's take an example here. So let's say we took that same example of the diagrams, which I was seeing earlier, and we have converted that, we have flattened it into a 1D array. So we've made it 1, 3, 5, 7, right? So this is our perimeter positions. Now our start is 1. Our maximum allowed is going to be 1 plus 8 because our perimeter is 8. 1 plus 8 minus, let's say our minimum distance is 2, right? So this is 9 minus 2, and so our maximum allowed start position will be at 7. So we chose a start, our start is 1. Now we're going to look for, after 1, we're going to look for, let's see here, right? This is 1. After 1, we're going to look for 3 more points because k is equal to 4. The question, we're going to look for 3 more points that they fall within this boundary of the last point being 7. And we're going to check for the remaining points. So we want to check if it's possible. Now, I want to find the next index that is possible if I go according to this. So why I'm doing a bisect left here on positions is what basically a bisect left is. It's asking for the lower bound. So the lower bound means the element which is either of the same value or the next greater value than the value we're trying to look for. So I say if I start from 1 and my minimum distance is 2, so 1 plus 2, I ideally want my next position to be at 3. Now there may or may not be a point at 3. That is why I take the bisect left instead of doing just a binary search on it. So I'm going to look for another value if it's on that number line in the position 3. So if I do this, it's going to go here, and on this, it's going to do a bisect left, which is our lower bound, and it's going to give me the index 1, which is for the value 3. Okay, so I do that, and it's possible. So I add my count. I do 1 plus 1, so now I'm able to fill 2 points, and the next value again, 3 plus 2. I go and search, and I do find 5, yes. So I'm going to add another 1, and again, I'm going to add another 1 for 7. So yeah, this is the ideal condition where it's actually working. Let's say my k was actually something like 5, and my next value after 7 was something like 8. Okay, so I would have gotten that value from bisect left. So no, actually I wouldn't get that value because bisect left would be looking for 7 plus 2, which is 9. And that 9 is not possible. So bisect left would by default give me a return value of n. So I do want to make sure that whatever I get in this next point index, if it is equal to n, or else if the value of that perimeter positions of that next point index is crossing the maximum limit that we had. And the maximum limit we had was, what was it? It was this over here, maximum allowed start. So if it's greater than our maximum allowed start, then we know that we're out of bounds, and definitely this this minimum distance is not possible, right? So if it's not possible, we return back to our we return back to our binary search over there, and we're going to return a false. So if it's false, we know that we have to reduce that kind of boundary that we're searching for binary search over there. So yeah, I hope this is clear. So if we just go through this can place function here, so what we're doing, yeah, we're starting from all positions. As I mentioned, we're going to mention our maximum allowed, which is start plus perimeter minus minimum distance. This is just to be cautious of the case that we we overlap, because this is a circular area in nature. We we have a count. So I'm going to look for k more points. I get the next index. If that next index is like, it's not possible, I'm just going to break out. And if I break from this loop, it's a return false by default. Or else I know that, so the current that I took here was actually the start value. So it's, if I look at that, so my start value would have been this. So it's a 1. So after doing 1 and I successfully am able to move to 3, I want to make 3 my current now. So 3 will be my current, and then 5 will be my current, and so on. So I have, I'm going to update that current, which is now going to be equal to perimeter positions of that next index, which I got here from bisect left. Yeah, so I keep doing that. And every time I find a valid value, I just go ahead and I add 1. And I'm also going to do this check because I don't really need more than k values, because it's asking us like we want to fit like k points, or can we fit more? That's possible as well. So if I immediately get that k is greater than count, then I want to return true. Okay. So again, we're going to check here. Is it possible? So let's say we got that value. It is possible. It's stored in best. And then we go on trying to increase that value of the minimum distance, which might not be possible, but we always have it stored in best. So yeah, eventually at the end of this, we just return best. So let's go ahead and look at the time complexity of this. So what we're doing is we're doing a binary search, and we're doing a binary search from 1 to side. So I can put the time complexity of this is it's a log of side, a log n, but here, since our maximum value is side, it's a log of side. And from this, I'm calling a can place. So let's look at the time complexity of how much time this is taking, okay? So first of all, we're starting for perimeter positions. And I know that perimeter positions here has n points. So I know that's going to be n into something, n points. And then for each point, it can be a starting position. I'm going to look for k points here. So that's going to be an n into k. And let's see what's happening within these, like search for k points. Okay, I'm doing this over here. So the bisect left is basically trying to find the lower bound, and lower bound amidst perimeter positions. And now I know perimeter positions has n values in it. So it's k times log of n. And yeah, that's basically what I'm doing here in this. All this adding stuff is not much. So n into k log n over here. And we also have this perimeter positions, which is going through n values. So we have O of n over here. And our space, the only space that we do kind of use is for this perimeter position. So overall space is O of n. So if I take everything together, it's going to be O of n plus O of, yeah, this is the major time here. It's going to be O of n plus O of log of side into whatever we got from here, n times k log n. Yeah, this value here. So if we look at the most dominant part of this, it's actually this O of log side into n times k log n. So we can just kind of ignore this n. But yeah, the space is O of n, and this is the optimal solution. So we can go ahead and submit it. Yeah, and it's working well. So I hope you guys understood this. It is a kind of complicated question, but it's really nice to learn about binary search and how we can use it for optimization. So yeah, if you have any feedback, just leave it in the comments, and happy coding.